Hello and welcome back to C++ Real-Time Audio Programming with Bela. We've been covering a series of topics related to creating synths and audio effects in the C++ programming language. Now today's lecture is a bit of a misnomer in that we're not going to be working in C++, nor in fact will we create any audio systems. However, we're going to take a deep dive into how our hardware actually works, and this will set us up nicely for the next lecture, in which we create very high-performance FIR filters taking advantage of the particular capabilities of the Bela hardware. In today's lecture, we're going to write code in assembly language, which is the form of programming which is the closest to what the hardware actually does. We're going to see the basics of how assembly language works and how to call assembly language code from our C++ program. We're then going to look a little bit at how to work with floating point numbers in assembly language, setting the stage for the next lecture. By the end of this lecture, you're going to make a series of example functions demonstrating your ability to work with assembly language code. As always, you can find the companion materials on GitHub. This lecture needs a Bela starter kit or a Bela mini starter kit, and no other electronic components. Now, when you work with assembly language, your code is by nature hardware specific. That means that you can run this assembly language code on other platforms that have an ARM processor, but you would not be able to run any of this code on an Intel processor, for example, most laptops. And this platform specificity is something that we need to keep in mind when we choose what language we program in. We have quite a number of options, of course. The lowest level possible way of coding is in machine code. This is literally the binary data that the processor executes to run your program. Now, in this era, nobody actually programs in machine code. We can instead program in assembly language, which is a human-readable form of the instructions that the processor executes. We have, of course, in this lecture series been working in C++. This is still a language which is relatively close to what the hardware actually does. However, C and C++ are portable between different hardware platforms. Finally, we might consider writing code in one of any number of higher-level interpreted languages like Python or JavaScript. Where C and C++ are compiled into machine code before it runs, these higher-level interpreted languages are typically compiled into something called a bytecode. The bytecode is a more compact and efficient representation of your program, but which is still portable enough to run on any platform. This is a whole topic unto itself, which we're not going to look at in this lecture series. Instead, we're going to stay focused on the very low-level questions of what our hardware is doing. As I said, machine code is the binary data that actually runs on the processor, and assembly language is effectively the literal translation of machine code into human-readable form. One line of assembly language will typically produce one instruction for the machine to execute, with just a few exceptions that we'll see later. The reason we write in assembly language is that it's the closest that we can get to what the hardware actually does. Compare that to a language like C++, where we can't be precisely sure what machine instructions are going to result from the lines of code that we write. So at this point, it's worth asking, what does our processor actually do? It does several things. A processor will perform arithmetic and logical operations, for example, adding and subtracting numbers, multiplying them, shifting bits, or performing Boolean operations like AND and OR. A processor will also load and store values from local memory. Any processor will also be capable of testing and branching on various conditions. Testing and branching form the basis of flow control, which we use for instructions like if, for, and while in C++. When we write C or C++ code, we then pass it to a compiler before we can run it. And the first thing the compiler does is turn that code into assembly language. It then passes it to what's called an assembler, which turns the assembly language into machine code which runs on the processor. So it's worth asking, under what circumstances might we want to write in C versus writing in assembly language? Some properties of assembly language are that it's the closest that we can get to the actual hardware. That means we always know what the processor is doing, and generally speaking, how long it takes. If you know how the processor works, it's possible to write extremely efficient code in assembly language. On the other hand, any code that you write is going to be CPU specific, meaning that your assembly language code will have to be rewritten for each new platform. Even something as foundational as a variable you need to implement yourself by moving data to or from memory, and functions and loops will need to be implemented out of basic branching instructions. By contrast, C is what we might call a procedural language. It still executes instructions in order, and it's similar to how hardware works, but there's no direct analogy to particular CPU instructions. That means that C code can be compiled to run on any CPU and any operating system, assuming you're only using standard libraries. C will give you higher-level constructs like variables, functions, and loops, and one line of C code could potentially produce many lines of assembly, or in fact no lines at all. This is entirely up to the compiler. In this lecture series, we've been working on Bela. To understand how to write assembly code for Bela, we need to understand what it's based on. Bela uses the BeagleBone Black single-board computer, which in turn is based on a system-on-chip from Texas Instruments. That system-on-chip uses an ARM Cortex-A8 processor running at 1 GHz. Our assembly language code needs to be targeted to this ARM processor. Now, in fact, there are many different types of ARM processors. Most of them are what are called 32-bit processors, though some more recent models are 64-bit processors. There are several large families of ARM processors. There are the microcontrollers, whose model numbers start with Cortex-M. For example, the Cortex-M0, which is a very low-power and cheap microcontroller, or the Cortex-M4, or even more recent Cortex-M7 microcontrollers, which have a more sophisticated architecture and even support optional floating-point instructions. Separately, there is a family of ARM application processors. These days, these are all known as the Cortex-A series of processors. Whereas all the ARM microcontrollers are 32-bit processors, some of the more recent application processors are 64 bits. We'll talk in a bit about what this means. Every ARM processor, whether it's a microcontroller or application processor, actually has quite a similar instruction set, though you'll find a few instructions which are present on some processors and not others. Bela, as we discussed, uses the Cortex-A8 processor. This is based on an instruction set called ARMv7A. So if you were to look up the details of how to write assembly language instructions for Bela, this is the instruction set that you need to be looking at. I've included a link to it in the companion materials. Let's take a look at a few of those instructions. Here we have a table of different assembly language instructions and their syntax. In this middle column, we can see the name of the instruction and the arguments that we pass to it. And in the right column, we see what the instruction actually does. So for example, the top row of the table, we see a set of add instructions. We have one instruction, which is add, ADD, and we have another instruction, add with carry, ADC. Each of these is a different assembly language instruction. Following the name of the instruction, you'll see these other designations like RD and RN. What do these things mean? Well, these represent different registers within the processor. What is a register? Let's have a look. First, let's talk about C and C++ again. In these languages, we work with variables. We've seen global variables that persist across a program, local variables that are declared within a particular function, and in each case, a variable is actually implemented as a slot somewhere in memory which holds a value. The type of the variable, for example int or float, tells us a couple things. First of all, it tells us how much memory should be allocated for that variable, and it also tells us how we should interpret the data that's stored in that memory. For example, on Bela, both int and float require 4 bytes or 32 bits of memory to store, but the interpretation of those bits is very different. C and C++ give us some low-level tools to work out how variables are stored in memory. For example, we can use the ampersand operator to get a pointer to a variable. The pointer is essentially the address in memory at which that variable is stored. So if we have a variable called x, writing ampersand x doesn't refer to the value that x has, it refers to the location in memory where x is stored. The inverse of the ampersand operator is the star operator, which dereferences a pointer. For example, if p holds an address in memory, star p tells the program to go to that address in memory and extract the value that is stored there. Now, all of this might seem quite nitty-gritty and abstract, but in fact, we've already been doing something quite similar throughout this lecture series. Whenever we work with arrays in C++, we use the square brackets to refer to particular elements of that array. What the square brackets actually do is very similar to the star operator. The array is stored as a series of consecutive elements in memory, and the square brackets tell us to go to a particular slot in memory starting at the address of the array, and this is how we retrieve a particular element of it. We'll come back to how this works more in the next lecture. Now, it's very nice in C and C++ to work with variables, but assembly language doesn't give us that, at least not directly. Instead, our operations are all going to work on registers. Registers are not locations in memory, they are instead slots within the CPU itself which can hold numerical values. Every ARM processor has 16 registers to work with. Other types of processors might have more or fewer. On the ARM architecture, mathematical operations, such as arithmetic and logical instructions, will always operate on registers for both their input and their output, with just a few exceptions that we'll cover later. So in the table of instructions that we saw a minute ago, RD and RN would refer to which of these 16 registers our instruction was operating on. Now, an obvious question is, what should we do if our program needs more than 16 values? Here what we do is we move the values between the registers and memory. The processor gives us two different types of instructions to do this. It gives us load instructions, which move data from memory into registers, and store instructions, which do the opposite. Now, given that C++ variables are typically stored in RAM, that means that a mathematical operation on variables might actually involve at least 3 instructions, loading the data from memory into a register, the arithmetic operation itself, and finally the store instruction to put the result back into memory. The compiler takes care of all of this, and it happens completely unseen to the programmer. A caveat, which is actually quite useful, is that the compiler might optimize your code such that your variables are only ever stored in registers. This is one reason why there's no penalty in a C program for declaring more names of variables as you go along. The compiler will work out the operations that need to be done. If you do need to use load and store instructions, these typically incur a delay, which might actually be considerably longer than the time it takes to actually do the mathematical calculations. This is because RAM is slower to access than the registers within the CPU. Now, all modern CPUs will have multiple levels of cache, which speeds up access to frequently used data. Still, if we're not careful in how we write our program, RAM access could actually become the bulk of the program's execution time. Let's look at a practical example. On the top, we have a single line of C code which adds 2 variables together. This compiles to 4 assembly language instructions. Notice from a syntax point of view that the instructions are all lowercase and that there are no semicolons needed at the end of lines. If we have comments, these begin with an @ character and continue through the end of the line. In this particular example, the assumption is that register R7 holds an address in memory, and that address in memory points to where the variable A is stored. In other words, R7 holds the number that we would get if we wrote the expression &A. We also assume that the variable B is located immediately next to A in memory. Typically, the C compiler keeps track of where the variables are stored and generates assembly code like this automatically. In this case, we have 2 load instructions, an add instruction, and a store instruction. The load instructions retrieve A and B from RAM and put them into registers R0 and R1. The add instruction then adds R0 and R1 together, storing the result in R0. Finally, the store instruction stores R0 back into RAM at the location of the variable A. We'll come back shortly to the format of these instructions. As we discussed, every ARM CPU has 16 different registers to work with. On 32-bit ARM processors, including the Cortex-A8 that powers Bela, each register is 32 bits or 4 bytes wide. What that means is that one int value fits into one register. Other C data types, for example the 64-bit long, might require 2 registers to store. Now, even though we have 16 registers, not all of them are available equivalently for our code. Some registers have special functions in the processor. R13 is the stack pointer. This tells us where the stack ends. This is a particular region in memory which our program will use for local variable storage. R14 is called the link register. It's typically used to tell our program where to go back to when a function call finishes. R15 is called the program counter. This tells the CPU where its next instruction should come from in memory. As a simple rule, do not mess with any of these 3 registers in assembly language, or your program is likely to collapse. On some operating systems, other registers will also be declared to have special functions, for example R7 and R9. If you're writing in assembly, you'll need to look up the particular conventions for the system that you're writing for. We can use the other registers as we like. However, in some cases, we need to restore their values when we're finished. Let's look back at this table of instructions again. Notice the format of the instruction. First we have the name of the instruction, then we have the register that will hold its output, and finally we have the inputs. In this case, the meaning of the add instruction is that register RD is equal to register RN plus this thing called operand 2. This operand 2 business comes up all over the place on ARM. What does this mean? Mathematical instructions on ARM processors are extremely flexible. Specifically, the second input argument to nearly every arithmetic and logical instruction can take several different forms. These are collectively known in the reference manuals as operand 2. Op2 could be one of several things. It could be an immediate value, which is to say a hard-coded number. It could be the name of a register, anything from R0 to R15. It could be a register which is bit shifted by a constant value, corresponding to the double less than or double greater than operators in C. Or it could even be a register bit shifted by another register. All of these things are implemented in the ARM CPU by a special circuit called a barrel shifter, which makes it very efficient to do these bit shifting operations. Here we see those options in tabular form taken from the reference manual. The beautiful part about this is that bit shifting doesn't actually require an additional instruction. It can happen as part of any of the other arithmetic or logical instructions. And then at the bottom here we see 4 examples. The first of them corresponds to R0 is equal to R1 minus the immediate value 1. The second of them adds registers R2 and R3 together, storing the result into R1. The third example uses the barrel shifter. It takes R1, shifts it left by 3 bits, and then adds R0, storing the result into R0. Mathematically, this is equivalent to saying R0 is equal to R0 plus R1 times 8. Notice that the bit shift happens before the addition. The last instruction takes the value of R1, bit shifts it right by 1, and stores it into R2. In general, bit shifting left corresponds to multiplying by 2 to the n, and bit shifting right corresponds to dividing by 2 to the n. So that's a basic overview of what assembly language looks like. Before we go much further, let's see some assembly language code in action. Remember that when we write our C or C++ code, we first run a compiler like GCC or Clang to turn it into assembly language code. We then run an assembler like AS or GAS, which builds the assembly code into machine code that actually runs on the processor. We can also write assembly language code directly in a file ending in .S. Next, have a look at the companion materials. You'll find a program called ASM test. This is a simple program containing 2 files. There's our usual render.cpp, and there's also a file called functions.s. The latter of these is written in ARM assembly language and has a simple function to add numbers together. We'll see shortly how to interface between C++ and assembly, but for now, just pause the video, run the code, and then have a quick look through it. Here's our first assembly language program. What it does is ridiculously simple. It just has 2 variables, which we call x and y. It adds them together using this function called addNumbers, and then it prints the result and it finishes. This instruction here in render tells the program to stop running, so we're not actually generating any audio at all here. Now, of course, we could have literally just written a plus sign in C++ and been done with it, but the point here is to understand what's happening in assembly language. The function addNumbers is declared not in render.cpp, but in this other source file called functions.s, so let's look at that now. At the top of the file, we have a number of lines which begin with a dot, like this one. These are not assembly language instructions themselves, they're directives to the assembler to tell it what kind of code to generate and how. I'm not going to talk about these now. You can basically use these lines as is in your own code. Instead, I'm going to focus on the assembly language instructions themselves, the main one of which is this, add R0, R0, R1. This means R0 is equal to R0 plus R1. Notice that I have, after the instruction, a comment on exactly what it does. I really want to emphasize the importance of commenting your code when you're writing in assembly language. In fact, I find in assembly language that it often helps to write the comments first, and then later work out exactly what instruction is needed to implement that particular comment. After the add instruction, we have this other instruction called bxlr. We'll return to what that means in a minute. It's crucial to making this into a function. For now, let's just run the program and see what happens. And there we go. X is equal to 3, y is equal to 4, z is equal to 7. Pretty straightforward. The tricky bit of that project was not the single add instruction, it was how to get data back and forth between C++ and assembly. We need a few things to call an assembly language function from C or C++. First of all, we need a few lines in the .s file. We saw some of those lines just now. There was one beginning .type, and there was one beginning .global. These 2 lines tell the assembler that there exists a function of this particular name which can be called. After those 2 lines, we need a label. A label is also not an assembly language instruction. It's just an indicator to the assembler that this is a place in memory that we might want our program to jump to. Finally, we need one specific assembly language instruction at the end of our function, which is called bxlr. In a C program, we don't need an explicit instruction to tell us to return from a function. Instead, when we reach the end of a set of curly braces, it will automatically go back to the caller. Here, we need to tell the processor to do that for us. The literal meaning of BXLR is branch with exchange to the link register. So BX is the name of the instruction. It is a branch instruction which tells the processor to jump to a different place in memory, and LR tells us where to go, which is the location stored in the link register. What will happen is that when our C program calls this function, it will store inside of LR where to come back to when the function is finished. In addition to those lines in the assembly file, we also need some mechanics to tell the C compiler where to find our function. We need to declare a prototype of the function at the top of our C or C++ file, or in a header file included from it. In this case, the prototype of our function is as follows: int add numbers, int argument A, int argument B. What that means is that we have a function that takes two integers as arguments and returns a single integer as a return value. When we declare this function prototype in C++, there's one extra bit of work that we need to do, which is to put it inside of a block declared extern C in quotes. This has to do with some subtleties of internal naming conventions in C++. Without this, you'd be able to call the function from a C file, but not from a C++ file. Now we see that this function has two arguments. It's easy to understand how to pass values into them, but where do they pop out inside of the assembly language file? By convention, the first four arguments of any assembly language function are stored in registers R0 through R3. That's assuming that they're of type int. It's a bit different if we're working with floats, and we'll come back to that. If you have more than 4 arguments, then extra arguments are going to be pushed to the stack, which is to say that they'll be stored at a particular location in memory that you can retrieve them from. We're not going to cover this. To return a value from assembly language is also relatively simple. All we need to do is store the value inside register R0, assuming it's of type int, and then return using BXLR. If we had a longer type, like long, we might split it across registers R0 and R1. That brings us then to the first coding task of this lecture. Go back to the ASM test project and make a new function called subNumbers. This function should subtract argument B from argument A. You'll need to declare a prototype of this function inside of render.cpp and then implement it inside of functions.s. It will need its own .type and .global directives, and it'll need its own label called subNumbers. You don't need to repeat those first 4 directives at the top of functions.s. One thing that you need to find out using the ARM instruction reference, which I've posted in the companion materials, is what is the name of the assembly language instruction to use for subtraction. I'll leave that to you to discover. Pause the video here and try implementing this. Okay then, let's look at the implementation of our subtraction function. Now I've actually only finished this example halfway because I want to show you what happens when we haven't quite made things line up between C and assembly. So I've completed the C++ part of this example. In that I have declared a new function prototype inside this extern C block. The name of the function is subNumbers, and notice that I'm also calling that function inside of setup. Now when I run this project, it's not actually going to work yet. You see there that in the final compilation step, which is called linking, the compiler tries to put together all of the different files that it's built, and here it encounters an error because it's looking for this function that we've declared called subNumbers. But up here what we have is only a prototype of a function. We're telling the compiler there exists a function called subNumbers, but we have not actually implemented it yet. And because I have not yet filled in functions.s to implement this function, you can see that the linker finds an error. It says undefined reference to subNumbers. If you had an error like this in C++ and you were positive that you'd implemented it in assembly language, make sure that your function prototype is inside one of these extern C blocks. That often solves the issue. But let's go over to functions.s and see what we need to do to implement another function. We saw before that we had various directives at the top of the file, which were just telling the assembler what to do with this text. And then the actual declaration of the addNumbers function was down here at the bottom. To make subNumbers, we effectively need to duplicate a lot of this text and adapt it for our new function. So I'm going to copy and paste this. Now we need to change addNumbers to subNumbers throughout. So we're going to change this .global statement, we're going to change the type, and we will change also the label. Remember, the label just refers to a particular instruction that the code might want to jump to. Now, of course, we don't want subnumbers to be adding our numbers together, so we need to find out what other instruction we should use. And if you were looking on the companion materials, you probably found that there's a subtraction instruction. It's called sub, so that's what we're going to do right here. Now, we're still not done because we need to remember what the order of arguments was. What was on the slides is that subnumbers should calculate b minus a. So let's write that out as a comment first. R0 is equal to R1 minus R0. Now we need to go back to the instruction set reference to figure out what order of registers is going to calculate that. In this case, what we want is sub R0, R1, R0, like that. This says R0 is equal to R1 minus R0. And that should do it. We can run this code and see if it works. And there we go. That's what we expect. 4 minus 3 is equal to 1. Next, having completed the subnumbers function, let's make one that's slightly more complicated. We're going to implement a function called add with shift. It takes 3 int arguments and returns an int. The equivalent expression in C is given here. We're going to take arg-a, add arg-b left shifted by 1, and add arg-c right shifted by 1. So our first question is going to be, how do these 3 arguments appear to our assembly language program? Well, we should know the answer. It's that they appear in registers R0 through R2. The next question is, where do we put the return value when our function is finished? Again, this is like before. The return value is stored inside of register R0. Next then, how should we implement the bit shifting? Well, we could find some bit shift instructions to run on the ARM processor, but remember that we have a better option, which is to actually make the bit shifts part of the add instruction itself using ARM's barrel shifter. To see how to format that, go back to the upRAN2 table in the reference materials. In this case, inside of setup, instead of calling add numbers or subnumbers, call add with shift, passing 3 arguments, x, y, and 8. Recall that x is equal to 3 and y is equal to 4, so what should the answer to this function be? You can think about that for a minute, or maybe try writing the expression in C so you can see what you expect to get, and then compare it with your assembly language function. Pause the video here and try this. Alright, let's have a look at this. As before, I've already implemented the C++ side of things. I've declared the function prototype add with shift. Notice that it takes 3 arguments rather than 2, and I've called it here inside of setup, passing it 3 numbers, x, y, and the constant number 8, as discussed on the slides. Now, we need to go across to functions.s to see how this is implemented. I've started out the function prototype here. Notice the .global and .type statements and also the label. Now what I've done here is I've written out the comments for what it is that we want to do. What we need to do is fill in the assembly language instructions that do this. So overall, this line shows us the entire calculation that we want to perform. But this addition of 3 quantities is more complicated than we can implement in a single assembly language instruction. So we're actually going to need to break it down into 2 smaller operations. You can probably guess that each of these operations is going to involve an add instruction. And there's also some bit shifting involved here. As we discussed, we don't need a separate instruction for bit shifting. Instead, we can use the ARM barrel shifter to do this. Let's start with the first one. This is going to be an add instruction. Its output register is R0, so that's the first parameter. The first of the inputs is also R0, so that's what comes next. And then the next thing we need to do is somehow calculate this quantity R2 right shifted by 1. Alright, we'll start with R2, but how do we do the right shift? Well, if you look in the reference at how to write this up to business, you'll find out that what we need to do is R2, and we use ASR 1. The hash sign is used to indicate the immediate decimal value 1. ASR stands for arithmetic shift right. This is the kind of shift that works with both positive and negative numbers. We won't look at that now, but you can find out more information in the reference manuals. The next instruction is then going to be similar. It's also going to be an add instruction. Its output's going to be R0, its first input will be R0, and its second input will be R1, but left shifted by 1. In this case, we can do a logical shift left by the immediate value 1, like so. Logical shift left means basically just move all the bits 1 slot to the left and fill in the last bit with a 0. This is equivalent to just multiplying the number by 2. Let's just clean up our formatting here so that everything's in a nice column, and we should be able to run this and see how it works. And there we go. Next, when we write functions in assembly language and call them from C or C++, we have a few more things to think about. Remember that the ARM CPU has exactly 16 registers to work with. Aside from the registers we're not supposed to touch under any circumstances, other registers might have been in use by our C program. We can't just have our assembly function arbitrarily change the value of any registers and then return, because it might cause our program to crash down the line. There's a convention which, if we respect, we can ensure our program will work properly. The convention says that within a function, we can change the values of registers R0 through R3 and register R12, and that we do not have to restore their values by the end of the function. Any other registers that we want to change, we can use temporarily as long as we put them back the way we found them. The easiest way to save the value of registers is to push and pop them from the stack being a special region in memory where we can temporarily store values. The way that looks is like this. The push instruction moves the value of the registers that we pass in into RAM, and then the pop instruction moves them back from RAM into the registers. Notice that we always pop things off the stack in the reverse order that we pushed it on. Here we see that a single push instruction can save up to 4 registers at a time to the stack. The syntax involves putting the register numbers inside of these curly braces. When we pop them off the stack later, notice that the order of the registers within the curly braces remains the same. The next important thing to think about in assembly language programming is how to deal with branching. We don't have useful constructs like if, for, and while inside of assembly language. Instead, we have to create them for ourselves out of branch instructions. Basically, think of a branch instruction as a go-to statement. For example, the instruction B, followed by the name of a label, will tell the CPU to jump to the code starting at that label. Now, labels themselves are not assembly language instructions. They're just a reference for the assembler so that the branch instructions know where to go. Declaring a label is pretty simple. We just write it on a line by itself with a name that we choose, and the name is followed by a colon. By convention, the labels have no indentation where the instructions after them are typically indented. In the example here, we have 4 assembly language instructions and 1 label. The first instruction loads a value from RAM into register R0. The second instruction is a branch instruction. It tells the CPU to jump to the instruction that immediately follows the label store result. What that means is that the add instruction will never run in this code example. Instead, it will go straight from the branch instruction to the store instruction at the end, storing the value of R0 back into RAM. Unconditional branching is not by itself all that useful. The place that branch instructions become very powerful is when they become conditional. A branch occurs only when a given condition is met. This forms the basis of our flow control, statements like if, for, and while. The ARM architecture supports 14 different conditions on which to branch. They're given in a table here. The mnemonic indicates the suffix that we add to the B instruction to tell it what kind of condition to branch on. For example, in the first line, BEQ would mean branch if equal. So if our instruction was BEQ my label, what that means is that the CPU should next jump to the code indicated by my label if and only if the last comparison returned an equality. Now, as I said, there are 14 different versions of this branch instruction. We could branch on equality, non-equality, minus, plus, greater than, less than, etc. But initially, looking at this code, it's actually kind of confusing. What exactly are we testing? In the previous example, we saw an instruction that was BEQ and the name of a label. That meant branch if equal to that label. Okay, but branch if what is equal? What is equal to what? Notice that the branch instruction, unlike an if statement, has no test built into it. It's not as if the branch instruction says branch if R0 is equal to 3. So how do we know what we're actually testing? Well, it turns out that what the branch instruction is doing is that it's branching based on something called the CPU status flags. The status flags are a special set of bits inside the processor which tell us certain things about the results of previous calculations. The implication is that the branch instruction is actually branching based on what happened in a previous instruction. So we have one instruction which is going to give us the test, and then the next instruction is going to branch conditionally on what the result of that test might have been. Now there's lots of different test instructions that we could use. Here at the bottom of the slide are a couple of them. For example, we could have a compare instruction. Compare a register to an operand to. Now we've seen operand 2 before. Remember, that could be a constant value, it could be another register, it could be a register bit shifted by a constant, etc. A similar instruction is called test, the main difference between compare and test being whether they're performing arithmetic or Boolean operations on the registers. Here's an example of how we might use that in practice. This code contains 3 assembly language instructions and 1 label. The first instruction compares r0 to the number 5. Literally what the compare instruction does is it calculates the value r0 minus 5, but rather than store the result r0 minus 5 into a register, it just updates the CPU status flags. That means that the next instruction, BLT, which stands for branch if less than, really means branch if r0 is less than 5. If r0 is indeed less than 5, then the next instruction will be skipped. Otherwise, we add 1 to register r0. Now look what we've done here. We have built an if statement. We've essentially written the C code, if r0 is greater than or equal to 5, then increment r0. However, notice that the form in assembly language is actually inverted compared to C. Effectively, the assembly language implementation of this C code is checking whether the condition is false, and if the condition is false, then it's going to skip over the part inside of the if statement. Just take a minute to look at these two forms of code and convince yourself that they're doing the same thing. The next thing we might ask is how would we implement an if-else pair like we have in C? Now, I'm not going to give you the answer to this straight away, but my hint to you is that you'll need a second label and also another branch statement, and that second branch statement will be a simple B, branch always, not a conditional branch. In fact, this is going to be the next task. In the ASM test project, I want you to make a new function called conditional numbers. And here you can see the specification of what it should do. It'll subtract argument b from argument a if a is greater than or equal to b. Otherwise, it'll add a and b if a is less than b. As before, you need to declare the prototype of this function inside render.cpp. It'll be exactly like add numbers is declared right now, and you'll need to implement the function inside of functions.s as you did before. That means that you need a new .type and .global statement. Now remember from the previous slide that you will need more labels inside of this function than just the name of the function itself. You might find it useful, like before, to write out a version in C just to make sure you understand what the answers should be, and also be sure to try your function with several different parameter values. Pause the video here and try it. Alright then, let's have a look at the branching example that we just made. The function we are writing is called conditional numbers, and I have declared a prototype of it here inside of this extern C block, and I am calling it here inside of setup. So notice that I'm calling it with x is equal to 3, y is equal to 4, so the second argument is greater than the first one. That'll be important for how it runs. Let's go over to functions.s and see how it's implemented. As before, I've written .global and .type directives and put a label at the beginning with the name of the function. Then after the label, we have our comparison and branching instructions. The first instruction is comparing r0 to r1. Literally what this is doing is subtracting r1 from r0 and updating the status flags, but not storing the result of that subtraction in any register. That sets us up for the next instruction, which is BLT. That stands for branch if less than. In this context, what that means is that the branch will take place if r0 is less than r1, i.e. if the first argument is less than the second one. If that branch is taken, the next instruction to execute will not be the sub instruction, but it will actually jump all the way down here to this label, is less, and the next instruction to execute will be the add instruction, which is adding the two arguments r0 and r1 together into r0. As you'll recall, r0 holds the return value of the function. After the add instruction, the CPU will move right on to the next instruction, which is this one, bxlr, that returns from the function. Now going back to the beginning again, suppose that r0 was not less than r1, so when we get to this BLT instruction, the comparison was false. Well, in that case, the CPU will proceed right on with the next instruction, which is this one, the sub instruction. This subtracts r1 from r0 and stores the result into r0. Now, it's this last instruction here which might be the least obvious. Why do we need a second branch instruction? This is an unconditional branch. It will always happen when we get here that the next instruction will be the one that follows the label is less done. The reason is that if we didn't have it, then this add instruction would run all the time, regardless of whether we wanted it to or not. So this combination of a conditional branch and an unconditional branch is what we need to make two different blocks of code, this one, and have only one of them run at any given time. We can run this code and see what happens. Again, we have x equals 3, y is equal to 4, so r0 is indeed less than r1, and the two of them are added together using this add instruction, and the result is 7. Now let's go change it to be the other way around, and we'll see what happens there. So instead of doing conditional numbers x, y, I'm going to do it with y and x. So now we're passing 4 and 3. We'll recompile and see what happens. There we go. The first argument is bigger than the second one in this case, so the two of them are subtracted, and the result is 1. The example we just saw effectively implemented an if-else pair. Next, we're going to see how to implement loops using assembly language. As before, all we have available for this is branching instructions. So the first simple version is how do we implement an infinite loop? Well, the simple answer is that instead of branching forward, we should branch backwards to an earlier label. This example will simply add 1 to R0 infinitely forever. What's more interesting than an infinite loop is, of course, a conditional loop, the kinds of things that we encounter in for or while statements in C. What we need to do here is also to branch backwards, but rather than using an unconditional branch, a simple B instruction, we should branch backwards using a conditional branch. For example, branch of equal, branch of greater than, any of those 14 conditions available to us. Here's an example of a loop that will run 10 times. Before the beginning of the loop, we load the value 10 into register R0. Inside of the loop, we decrement R0 by 1. We then do a comparison instruction between R0 and 0. If R0 is greater than 0, then we branch backwards to loop start and run it all over again. Now, the ARM processor gives us one little trick that we can use to make this loop more efficient, and that is that we can add an S to the end of an arithmetic or logical instruction to tell that instruction to update the CPU status flags. What this means is that we no longer need the compare statement, we can just run sub S. What this will do is after we subtract the number 1 from R0, the status flags will be updated according to the result. Now, I'm working up to another example project here, and I want to look at a different category of instructions on the ARM processor. Every ARM CPU supports various multiplication instructions. There are multiplication instructions which are signed, which is to say they can take positive or negative values, and there are also unsigned values, which are always positive. We have standard multiply instructions, which effectively multiply one register by another, and then there are also multiply and accumulate instructions, which multiply two registers together and add them to a third register. The multiply and accumulate turns out to be a very useful concept for digital signal processing. Most ARM cores support 32-bit multiplications as well as some smaller sizes. Now, if you needed to multiply two 64-bit numbers together, some of the newer ARM cores will give this to you, but if you needed to do this on Bela, there is not a single instruction that would do this for you. Instead, you would have to implement it yourself by using several different 32-bit multiplies and then adding the results together in the right format. When you write C code using 64-bit numbers, the compiler does this automatically for you, so there's no sense in which running on a 32-bit platform means that you can't work with 64-bit numbers, it's just slightly less efficient to do so. Now, the multiplication instruction on the ARM processor has a slightly peculiar limitation, which is that the output register, RD, cannot be the same as the first of the input registers, RM. So you can write an instruction that says R0 is equal to R1 times R0, but you cannot write R0 is equal to R0 times R1. If you try to do this, the assembler will give you an error. In practice, this isn't much of a constraint since you can always turn the order of operations around, but it's just something to remember. This caveat also applies only to integer multiplications. We'll look at floating point multiplications later on. Now, if you look carefully at the instruction table for the Cortex-A8 processor, you might wonder where the integer divide instruction is. In fact, there isn't one. This would need to be emulated with a variety of arithmetic and logical operations, which could potentially be quite slow. However, some other ARM cores do have integer division, so these are the kinds of things that you need to look up when writing assembly language. This brings us then to another assembly coding task. In the companion materials, there's a project called ASM Factorial. The idea of this project is going to be to write a factorial function in assembly language. X factorial, as you might recall, is x times x minus 1 times x minus 2, etc., all the way down to 1. So for example, 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24, etc. The C code for calculating a factorial is already given in render.cpp, so you know what the right answer should be. Your challenge is to write the same code in assembly language. Now, just a few hints as you set out on this task. The input argument to the factorial function is given to you in register R0. The return value will also be in register R0. Now you might find it useful to accumulate your result into R0 as you go along, multiplying it by successively smaller numbers. However, you don't want to lose sight of that first parameter that you had, so what you're going to need to do is first move R0 into a different register so that you can then use R0 to hold your result. The move instruction is useful here. It just copies a value from one register into another. You can also use the move statement to load immediate numbers into registers. Remember that you can modify any of R0 through R3 and you do not have to restore them at the end. See if you can limit your code to only using those registers. To calculate a factorial, you're going to need a multiplication instruction, of course, and you're also going to need to write a conditional loop, as we saw a moment ago. I think you'll find the sub-s instruction quite helpful for counting down from your initial parameter toward 0. Okay, so take a moment then and see if you can write this factorial function in assembly language. Pause the video here and then we'll look at it. Okay then, here is our complete factorial program. Now, nothing has changed compared to the example in the C++ code. Notice that I have two different versions of this function. One is implemented in C, and the other is in assembly language implemented in factorial.s. The idea behind this sort of thing is that in some cases we might expect that our assembly version could be more efficient, but it's going to be much easier to write bugs in assembly language compared to C. So therefore, we write the C version so we can always compare the two of them against one another. This would let us write a unit test, for example, which would verify that the function was doing exactly what we thought it was. So I'm not going to go over the C code in detail, except to say that it's calculating this expression here, which of course is the formula for a factorial. Inside of setup, we're calling the C version of the function, printing the result, then calling the assembly language version and printing that result. Ideally, they should be the same if we've done our job right. We can go over to factorial.s and see how this is implemented. And here is our factorial assembly language function called factorial in ASM. Note that that matches the declaration of the function prototype in render.cpp. And I filled in all of the instructions that we need to implement the factorial. Let's look at this line by line. The first thing that we're doing is we're taking R0, which is the input argument, and we're moving it out of the way. The move instruction is actually better described as a copy. It's taking the contents of R0 and copying it into register R1. What that means is now we can reuse R0 to start accumulating our result, which we're eventually going to return at the end of the function. So the next line assigns the constant number 1 into register R0. We're going to multiply this by a succession of different values. We have to do a sanity check at the beginning of this function because the factorial algorithm only makes sense if the input is greater than 0. So we do this compare instruction, comparing R1 to 0. Remember, R1 is now the register that holds our input argument. And then we use this instruction here, BLE. BLE stands for branch if less than or equal to. In other words, if R1 is less than or equal to 0, what we're going to do is we're going to jump ahead to this label here, factorial done, skipping over the entire loop and just running this instruction bxlr, which returns from the function. Assuming that that's not the case, which is to say assuming that the parameter is 1 or greater, we're going to find ourselves inside of this block of code called factorial loop. That will first run this instruction here, which is a multiply instruction. We're saying R0 is equal to R0 times R1. Remember that the multiply instruction has this slightly peculiar constraint where the first input cannot be the same register as the output. After we've multiplied R0, then what we're going to do is subtract 1 from R1. We use the sub-s instruction here because this will update the status flags of the CPU. This means that we don't need to run a separate compare instruction. Instead, we can go straight on to this conditional branch instruction. BGT stands for branch if greater than. What that means is branch if R1 is greater than 0. The place we're branching to is back upward to the factorial loop. So we're effectively writing a while loop here. This code is going to run in a loop as long as R1 is greater than 0. And each time R1 gets smaller by 1 and then is multiplied into R0. That's how the factorial calculation runs. Once this condition is no longer true, then we're going to fall through into the next line, which is represented here. And the next instruction will be bxlr. Once again, that returns from the function. Remember that the return value of the function is going to be stored in register R0. Fortunately, we've been working with R0 this whole time, so we don't have to do anything special to move that into place. So that's it. We can run the code and we can see if it does what we expect. Great. Great, there we go. 6 factorial is equal to 720, and the C and assembly language versions of this function agree. Now we could try a few different other values just to make sure that it's behaving as we expect. So we'll go over here to render.cpp. I don't know, let's try 9 factorial, say. Compile it again, and run it again. And we can see that we get the same answer again. And then let's try a value that is not valid, like let's say 0. 0 factorial mathematically is defined to have the value 1, but our code needs to detect it specifically. So let's see if that's working. And it is. Great. So there we have it. One thing you might have noticed in the examples thus far is that we've always been working with integer or whole number data. All of the assembly language instructions we've seen so far only work with ints. For the final part of this lecture, we'll see how to work with floating point numbers in assembly language. The first thing to understand is that the ARM Cortex-A processors actually have 2 different types of FPU on board. The first of these is called the Vector Floating Point Unit, or VFP. Now, ironically, despite the name, the VFP is actually not a vector processor, in that it does not perform parallel calculations on multiple pieces of data at once. Instead, it's a classic scalar floating point unit which can do all of the usual floating point operations, but on one number at a time. The VFP supports both single and double precision floating point numbers, and on the ARM Cortex-A8 used in Bela, the version we find is called VFP v3 Lite. That means that the FPU supports the v3 instruction set, but the way those instructions are implemented in hardware saves chip area, but is slower to execute than a full VFP v3 implementation. There's also another floating point unit on the Cortex-A8. This is called the Neon. The Neon supports what are called SIMD instructions, single instruction, multiple data. These are true vector-based calculations for int and for float data. For example, in a single instruction, the Neon can multiply 4 floats by 4 other floats, which can make your code significantly more efficient to run. In this lecture, we're going to look at working with the VFP. In the next lecture, we'll see what we can do with Neon. And typically, in C++, if your code works with floats, the compiler will usually generate VFP instructions for that. If your code uses variables of type double, then VFP is actually your only hardware option, because the Neon does not support double precision. The VFP floating point unit is a separate part of the processor, and it has its own instruction set compared to the main ARM core. In the companion materials, you can find a link to this instruction set. You can see here that we have many of the familiar mathematical instructions like addition, subtraction, multiplication, and division, and also an instruction for calculating the square root. In this table, you see that the instructions are preceded by this little designation P in angle braces. In your code, this P will be replaced by one or the other of .f32 or .f64. This tells us whether the instruction will work on single or double precision. Another nifty trick is that VFP instructions can be made conditional. We saw earlier how the branch instruction could be made conditional by appending various condition codes. In fact, this works with nearly every ARM instruction. To understand how to use the instructions, we need to know a little bit more about the VFP core. The VFP has its own set of registers which are entirely separate from the ARM registers. The ARM registers are numbered R0 through R15, and the VFP has 32 registers numbered S0 to S31. Each of these is a 32-bit single precision floating point register. The VFP can also treat these 32 single precision registers as 16 double precision 64-bit registers. When we work with them this way, they're designated D0 through D15. This is just the same register storage, but accessed in a different way. In the VFP v3 instruction set, there are also 16 further double precision registers, which are designated D16 to D31. You can use these for double precision calculations only. To use the VFP, we need to understand how to get data into and out of its registers. Remember that when we called assembly language functions from C, we passed the arguments in registers R0 through R3, and the return value came back in R0. But what do we do if our arguments are not ints but floats? This turns out to be a more subtle question than you might expect, because it depends on a property of the operating system known as the ABI, or Application Binary Interface. This is basically an agreed-upon standard for programs to call different functions. It needs to be shared across the entire OS, all the libraries, and all the programs. For many years, the standard ABI on ARM Linux was something called SoftFP. SoftFP stands for Soft Floating Point, and what it means is that floating point data, when passed to a function, is going to still come in on the standard ARM registers R0 through R3, and the return value will come back in R0, just like it was an int. As programmers, that generates extra work for us because it means that when we want to do floating point calculations, we need to move the data out of the R registers into the S registers in the VFP, and when we're done with our calculations, we have to move the data back into the R registers. So in this simple example, it's actually bought us 3 extra instructions of type vmove. Now moving data from the R registers to the VFP registers is quite fast, but going the other way around can actually be extremely slow, taking 20 or more clock cycles. This means a big performance hit to your program if you're calling functions involving floats many times per second. Now you might reasonably ask, why would we saddle ourselves with such a slow and elaborate way of passing floating point data back and forth? The reason is that code compiled for the SoftFP API can also run on CPUs that don't have a floating point unit at all. The floating point instructions can just be emulated. The alternative, which is used on Bela, is a hardware floating point API called ARMHF. This version is actually much simpler. Floating point arguments come in directly on the VFP registers S0 through S3, and a float return value will be returned on register S0. If you mix int and float arguments, then it'll use a combination of ARM and VFP registers. The big advantage of this is that there's no extra moves needed to go back and forth between the R and the S registers, but ARMHF code is not capable of running at all on systems that don't have an FPU. This brings us to the final task of this lecture. In the companion materials, you'll find a project called ASM Float. This project gives you a template function for calculating the Euclidean distance between 2 points in space. Your job is to implement the assembly language instructions needed to calculate this equation. As I mentioned before, I suggest that you actually write out comments first about the order in which you want to do these calculations, and then only once the comments are written do you write the assembly language instructions to implement it. Pause the video here and give it a try. Alright then, here we have our floating point code in assembly. Now there's actually 2 functions that I've declared here. One of them was already implemented for you just to show you how it works, and then the other one was yours to implement. The simplest one, which was done for you, was called multiply floats ASM. This is basically just multiplying a times b, nothing fancy there. And then the distance function is the one that you're supposed to have implemented. You can see down here inside of setup the same kind of idea in terms of comparing C and assembly language versions of the functions, and then also calculating the distance function here and printing the results. The interesting bits here are all happening inside of functions.s, so let's head over there. Now there's one thing that we needed to specify at the top of the file for this to work, and that is to specify the FPU that we're using. In this case, VFP v3-D16. That's the version of the VFP that we find on the Cortex-A8 processor. Then down below we have the declaration of our functions, as we did before. So this first function is called multiply floats ASM. Again, what it's doing is just this single line here, which is multiplying 2 floats by one another. Notice we're using the instruction vmul, which is a floating point multiply. We can see by the suffix .f32 that we want a single precision multiplication. We're multiplying registers S0 and S1 and storing the result into register S0. Now, assuming that we're using the hard floating point ARMHF ABI, as we discussed, then you don't actually need to do anything else inside of this function. The arguments are coming in on S0 and S1, and the return value is coming back on S0. If you were using the SoftFP ABI, you'd need to also have these lines here, moving values from the R registers into the S registers and doing the same thing when you're done. That then brings us to the implementation task of this particular example, which is to implement this function called distance. I've written in comments here what mathematical expression we actually want to calculate. We need to know a few things. First of all, we need to remember which of those arguments was in which register. So in this case, S0, S1 corresponded to X1 and Y1, S2, S3 correspond to X2 and Y2. Now, I previously recommended that before you write out any lines of assembly whatsoever, the first thing you do is write out a series of comments, because the most challenging part of implementing this function is not looking up instructions in the reference manual, it's figuring out how to break down a relatively complicated mathematical expression into a series of primitive operations that you can calculate using individual instructions. So let's see what I'm doing mathematically. First, I'm calculating x2 minus x1 and storing that in register S0. Next, I'm taking y2 minus y1 and storing that in register S1. I can then proceed to take the square of each of those two quantities, storing them back into the same registers. A square, of course, is just multiplying a number by itself, so I use a multiply instruction for that. Finally, once I've squared each of those quantities, then I can add them together, storing them back into register S0. And then finally, once all of that's done, then I can take the square root. The result has been stored into S0, and that's exactly where the return value should be, so at that point all I need to do is return from the function. Basically what this code required of me was to remember the order of operations in mathematics, the kind of thing that the C compiler would do for you, but you need to implement for yourself in assembly language. If I'd wanted to, I could have done something very similar with type double by using the .f64 extension to the instructions rather than .f32, and changing which registers I used accordingly. But we can just run this and make sure that it works as we expect. And there we go. You can see that the simple multiply instruction produces the same result as C, and in fact that distance calculation is correct. So that's it. We've shown that we can work with a VFP in assembly language. And that brings us to the end of this lecture. This has been a basic introduction to working with assembly language on ARM processors, including working with integers and floating point numbers, and making conditionals and loops out of branching instructions. In the next lecture, we'll see how to apply this knowledge to audio signal processing, and we'll get into working with the neon unit, which, as we'll see, can give us a major speedup in our audio code. Until then, don't forget to subscribe to be notified of all of our latest videos, or drop by any of our online or social media resources. Thanks as always for following along, and we'll see you again soon.